Tech Topical, Tech's best talk show. Tech Topical, tell me what's the topic, yo. Tech Topical, talk tech topic show. Tech to the topic. Hello, everyone, and welcome to Tech Topical, Tech's best talking show. I am your host, Brian Ross, and today, well, let me give you some context, because today we are going to be doing one of the most technical things that anyone's ever done ever, and it's never been done before, at least that I know of, and it's going to be exciting, and you're going to get a lot out of it, I hope, because today we are looking at a talk given by a Princeton PhD in front of a whole bunch of other Harvard PhDs in a big building that I'm assuming costs millions of bucks to make for the sole purpose of educating the other intellectually enlightened, I'm sure, as they would like to think, people of society. And we are going to dive straight into the middle of it and then get... Oh, we got some people in chat. Right. We're going to drive straight into the middle of it and then get all of this useful information out. And I'm going to explain to you what exactly these people are talking about, because it can get a little bit tricky, but it's kind of a bit of a how should I say it? It's something where, for those people out there who may be learning something technical, one of the things that can be very intimidating is watching other people who seem to know way more than you talk about things in language that you don't really quite understand. They're going to be throwing some big words around, some big terms. And luckily today I have not just me, but I have another mind to kick this around with. I have another expert here with me today. And what do you get when a Middle Eastern country is born in Spain? That's right. You get what? Data science concentration student at Make School, Jordan Torres. Welcome today, Jordan. How are you doing?
Wow, what an introduction. That was beautiful. Thanks for having me.
Yeah, do you like, because Fernando Torres, he was Spain. Anyway, welcome, Jordan. And Jordan's going to be helping me figure all of this out. And let's go ahead and see what's going on in the chat. We got Thoughts on the Ground. Jordan's here. Thoughts on the Ground's very happy that you're here, Jordan. They say wonderful things about you all the time. JT, as some may call him, he is... He's bringing cute back, not like the other JT. Anyway, so here's the topic for today. It's, of course, machine learning for material discovery. And why material discovery, you may be asking? Well, I'm going to tell you, and that's because of a few things that we're going to learn during the video. I have taken a peek before, so I kind of know what we're getting into. But one of the things that's so interesting to me is that we want to take machine learning and be able to apply it across different concentrations and different breadths, regardless of what the reality of our situation is in regards to how much data we have. Because Jordan, you'll back me up on this, right? In order to do machine learning, you need to have a bunch of data points. Normally, that's how people think of it, right?
No, definitely. I mean, it's getting all this information, training it, making it learn this one thing to predict the same thing. But when we're talking about it in the material discovery, from what I have looked into and what you've sent me, what we're going to see, it's done a little differently, and it's really interesting on how they're approaching it.
It's done a little bit differently. Really interesting how they're approaching it. You are 100% correct. At least I think so, Jordan. So let's go ahead and see what's going on. This was a talk given at the let me get ready. This was a talk given at the Harvard John A. Paulson School of Engineering and Applied Sciences at the Institute for Applied Computational Science. This talk is titled Machine Learning for Materials Discovery by Dr. Julia Ling, Director of Data Science at Citrine Informatics. 2018, so you'll see no one wearing masks. No, how could they? And let's go ahead and start hitting play. Let's just go right into it. Let's see what we're getting ourselves into. I hope you find this interesting, because I did. I sat here and watched a few times. Anyway, let's see what's going on. Let me know if you can hear it, chat.
Hi, everyone. So we'll get started now. My name is David Sondak. I'm a lecturer in computational science.
Also, it's a long video, so I'm going to play at 1.25 speed, and we're not going to watch the whole thing. Yeah, let's just do 1.25 speed.
In IECS here at Harvard. And thank you for coming to our very last IECS seminar for the year of 2018. That's really the only announcement for today. We'll pick up again in the spring session. So thank you all for participating, and we look forward to seeing you all again. But
Jordan, do you think I kind of look like this guy?
See, I didn't want to say it, but since you brought it up, it's fair game now. Yeah,
like a little bit.
Like, no wonder he loves this video so much. He was there.
Before we end, we have to introduce our final speaker, Julia Ling. She's the director of data science at Citrine Informatics. She did a bachelor's in at Princeton in physics, a PhD in mechanical engineering from Stanford University, and
bachelor's at Princeton, PhD from Stanford. Does that impress you, Jordan?
Maybe one more degree would have been better, but I can suffice with those right now. I really think, maybe underqualified, maybe. Who am I to say? I don't have the first degree, so 2 might be enough. We'll find out.
Yeah. Well.
After that, she was the Harry S. Truman Fellow at Sandia National Labs. Now, that's about the time when I met Julia at various conferences, and at that time she was doing fluid mechanics just like I was, and then she's since switched to material science, as you see from the title of her talk. Maybe one day she'll come back to us in fluids, but for now, material science. So let's give a nice introduction, or welcome to Julia, and she's going to talk about machine learning.
I know that was a throwaway line, but I think that that's kind of interesting in that modeling fluid versus modeling materials. I think that's super interesting because you never think of modeling different states of matter. You think about modeling maybe data analytics, or you think about modeling clicks, or you think about modeling other things. Mm-hmm. But then to think about how we're going to be modeling physical objects in machine learning, that's pretty interesting to me, because that's kind of where a lot of the use cases I would think are going to be happening. Like when you are playing a computer in like a video game, like let's say chess, and the computer, it's that type of game where the computer is just super OP and way better than any human because they can react super fast.
Yeah.
Like we kind of want that computational power to be happening with our things in real life. And I don't know, I hadn't ever heard of someone working on a machine learning for those types of physical material purposes. Have you, Jordan? Have I missed that?
All of the machine learning I've ever looked into was mostly game related, or autonomous vehicles and kind of stuff. So thinking about it in the perspective of materials is really interesting, because the way that a liquid is formed and the way that it can learn about a liquid is completely different from something else, some solid form of matter, a gas. So finding materials and training it to understand the specific values of a material is something I didn't even think about when listening to the video the first time.
Yeah, very interesting. Let's see. Let's keep going. Let's see what I'm saying. Oh, I'm done talking. Okay.
Thanks for that introduction, David.
No problem.
Can everyone hear me in the back?
Yes.
Perfect.
Awesome.
So yeah, as David said, my name is Julia Ling, and today my talk is focused on machine learning for materials discovery. But as he mentioned, my background is not actually in material science, it's in turbulence modeling, and my interest more broadly is in what happens when you apply these data-driven methods to physical systems. How can you integrate?
Okay, see, that's one of those things I'm talking about. That's one of the PhD lines where they can say something, I can say something, and then they can say completely differently. And then when they say it, you have no idea what's going on. So, closed captions. Yeah, I'll put closed captions on the video.
Next to it. The CC.
Okay, CC. There it is. Physical systems. All right, hold on. I just want to rewind this real quick. Oh, that's going to make it full screen. Is that okay? Yeah, I'm sure it is. So let me look at this again, this time with closed captioning.
My background is not actually in material science, it's in turbulence modeling, and my interest more broadly is in what happens when you apply these data-driven methods to physical systems. How can you...
All right, what happens when you apply these data-driven methods to physical systems? That's like what we literally just said, Jordan, taking the machine learning for physical things. So that's what that means. And then I'm not a material science person. I'm a turbulence modeling person. And of course, turbulence is sort of, you could think of it like, a plane where there's turbulence and it's kind of like fluid and there's a pressure systems going on. So it's modeling that sort of thing. It's not like a physical thing, but it is sort of a physical thing. Anyway, that's what Julia Ling specializes in, is this displacement sort of thing, but now she's going to take it instead of that fluid sort of area, we're going to go into a material, like a physical thing, like a good desk or something, like the materials that make a good desk. That's what we're going to do, and we're going to do it with data. We're not just going to be winging it. We're going to be doing it with data. So that's what I think she's talking about there. Does that make sense to you, Jordan?
Well, yeah, sure.
Yeah, because
it's,
let's keep going.
Yeah.
What do you think? What do you think?
I think we should keep going. It's
okay.
Integrate domain knowledge
we're only a minute in.
into these models. How can you get interpretability out of them?
Interpretability,
and so a lot of the
we'll get
lessons
back to
that we'll talk about, the lessons and the challenges from this work, are pretty broadly applicable to other applications in the physical sciences as well.
Cool.
Oh, and if people have questions, feel free to raise your hand and interrupt me at any point.
I'll interrupt you right now because I think I've seen the same template on Google Slides. No matter what level you get to, you're going to Google Slides for your slides, Jordan.
It's free. It's I mean, if it's not broke, don't fix it. And I mean, it's the new classic right now. Microsoft Word and PowerPoint and everything, it's old school. If you're not on Drive, you're not doing it right.
If it's free, it's for me.
So I'll just start by saying, why do we need machine learning for materials research and development? The first is that we have very high dimensional design spaces. In a typical research materials development problem, you can think about looking over a very wide variety of different compositional spaces with different elements. And then also there's a lot of processing parameters. So if you're not in materials, then there's things like heat treatments, solution treatments, et cetera, that you might want to vary. And so you have to figure out how to explore that design space in a systematic way.
See, she did it again. Systematically explore high dimensional design spaces. To me, tell me if I'm close. To me, that means that we have to be modeling this whatever it is that we're modeling. It has to work in like 3 dimensions, like an actual physical thing.
Mm-hmm.
Whereas my model for recognizing like an emoji or my model for recognizing something on a computer, like that's 2D. So it's a little bit simpler. So now we're going to move into 3D. That's what all of that meant right there.
And furthermore, you want to use the data you're generating as you collect it. You don't want to have to wait to generate 50 data points before you can do something meaningful with it. Every time you take a new data point, you want that to immediately be useful and to recognize that value.
We're good there, right, Jordan?
Yeah, I like what she's saying about that.
It's interesting.
Yeah. Because when I'm hearing that, that means, I mean, it's if that was applied to anything, that just means that when I made a model with one of my classmates previously, shout out to her, she's amazing, but that model had so many different data points and we had to train it on so many. And I feel like, yes, they're all useful, but being able to like actively get these new points and make them useful is something that I think is super interesting and something that should be like explored more, because it whenever I hear about making a model, it's always like thousands and thousands and thousands of data points, and they all need to be used all the time, and it needs to learn this and this and this. And if it doesn't, then it'll crash. But she's trying to make it seem like this data is going to be leveraged every single time, and it's going to be making a difference. Maybe it's happening the same way we make our 2D models, but hearing it like this and hopefully getting more information on this makes it sound really interesting.
Yeah, I think you put it absolutely perfectly. Yeah, that makes sense to me.
One of the other things we often have in the sciences is we have a lot of different sources of data. Often we have both computational data as well as experimental data, and it's not always clear how to use those together. Sometimes we'll have information at the micro scale as well as at the macro scale, and again, it's not always clear how those match up. And so machine learning can be used to try to glue together those heterogeneous data sources. And
Heterogeneous data sources. I promise I'll stop stopping at something. No, I don't promise that. I'm going to keep stopping it.
Don't promises.
Heterogeneous data means data that is not all alike. So like click data. If I go onto a website and like I'm taking data from people on a website, that's all click data because I'm seeing what they're clicking. So that's homogeneous because it's all the same. And then heterogeneous is like I have like an experiment that was done in Switzerland on this physical object in 2005. And then I have some other like machine learning predictions that was done by a PhD doctoral person. And then I have all these different sources of data and all of their inputs kind of look differently. They're not all the same. They're not all one nice, neat type of data that we can do stuff on. I think that's pretty interesting. What do we think about this in the chat? Thoughts underground with the nice purple heart. I give you a huge purple heart back. Bam. Support the troops. Let's go.
Talk a little bit more about what I mean by that in particular later in this talk. And then the overarching goal here is to try to accelerate materials discovery. It can take years to decades to develop new materials, and that's just too slow. If a new iPhone comes out every year, then they want a stronger glass every year so that, I mean, they do want it so that you don't break it every time you drop it. It doesn't always seem that way, but...
I don't agree with her. I don't think Apple cares if I break my phone. I think they want me to. That's my conspiracy for today, Jordan. What do you think?
It's not a conspiracy. I'm pretty sure it's fact.
If they wanted to make an unbreakable iPhone, they absolutely could. You just take one of those OtterBox cases, like you build the iPhone, and then you just build the case around it, and there you go. I don't know.
I mean,
they have more and more.
If we're going to get into that, that's a whole different tech. That's supply and demand and the way that they're trying to push people out to buy the latest and greatest by making things not as good. We'll save that for next week, guys. Please tune in.
Curse you, Tim Apple.
Demanding specifications for the glasses on these different projects and for the materials in these different products. And so that's the motivation for why we need to accelerate materials discovery, is just the demand is there.
Right. We want to make new stuff
easier. So then the question is, why is this hard?
Me.
Why can't we just, I mean, machine learning, artificial intelligence, these have been broadly applied for ad tech, for e-commerce for so long. Why can't we just take those same tools and transplant them onto material science? Well, there's a few challenges in materials that are just different from traditional machine learning applications. And so I've listed 6 of them here, and the bulk of my presentation is going to be going into each of these in more depth and really diving into what I mean by that challenge and how we approach it at Citrine. Maybe I should have said at the top, so I work at this startup called Citrine Informatics. We're based out of the Bay Area. We're about 45 people, and our goal is to try to bring data science and data management to material science.
Citrine, yay, Citrine.
And so
Bay Area.
In terms of these challenges,
Love that
the first
area.
one is in data type.
Same.
So it's true that in traditional machine learning applications, you might have heterogeneous data. Often you don't. If you're working with click data, then all the data you have is click data.
Yeah, click data.
Materials
I was just talking about click data. She said click data. How about that? Not making it up. If you can't see Twitch chat, let me know. Check out, all right, Thoughts Underground says, check out the Open Catalyst project if you're interested in some cool machine learning to accelerate chemical discoveries, similar to what she's talking about, accelerating materials discovery, as well as machine learning applications for pharmaceutical development. Really cool stuff. I would agree that is really cool stuff. And this is exactly sort of, I think, in the same vein, because, you know, when we're looking at putting together different types of material, and I guess we'll go over the slide just in case you can't see it. Or maybe if you put your face like really close, you can see it. But no, that's exactly right. I think that that's super interesting. And I think later on, we're going to be talking about how we can get this sort of chemical data and into a useful form, a useful like code for us to do some machine learning on. And because materials discovery, it's really kind of that. I mean, everything's chemicals, Jordan. You just put different chemicals together and you get new stuff. And that's kind of what we're looking at here for new materials is what chemicals do we need to combine to make the thing that we want to make. Does that make sense, Jordan?
Yeah, it's machine learning alchemy.
Machine learning alchemy. No, that is exactly right. I've been telling everyone it's alchemy. Yeah, no, it's exactly it. All right, let's see here. So we have 1, 2, 3, 4, 5, 6. All right. Why is machine learning for materials R&D hard? If we understand this part, if we can understand why it's hard, then I think we understand a lot about 1, machine learning, and then we understand a lot about 2, materials science. If we can like just extrapolate from here, you'll see what I mean.
It is highly heterogeneous. We get it from a lot of different sources in a lot of different formats. And it typically requires extensive feature engineering. So feature engineering is what you do to get from your raw data to something that's useful for machine learning. So if your raw data is an SEM image, then that might not be readily usable for machine learning without any kind of transformation.
SEM
The next one is data volume. In a lot of AI applications or machine learning applications, they're talking about millions or billions of data points. That's just not the case in materials science. Our data sets are small. Sometimes we're talking about 100 data points, sometimes less. You can't just...
we were talking about that earlier. So normally we have billions and billions of data points, or at least millions. In here, we have like maybe 100 data points or something, like a couple hundred, if that, maybe less. That's a huge paradigm shift for what I've always thought about as traditional machine learning. Normally, and I think traditionally, data has been king. The more data you have, the happier you are in life, and the more accomplished you are in life. If you just have the data, you can do whatever you want with it. But here we're going, we're kind of like venturing into the unknown. Doesn't it kind of feel like that, Jordan?
It's fun though. I mean, just reading the slide, I'm not sure if everyone can see it, but reading all of the things that machine learning applications need, it's restricting, but at the same time, using that specific set of rules can help us find new things. And I think it's really interesting with just that limited data set, we could find ways, like you said, to mix a bunch of stuff together and make something completely new.
Because it shouldn't work. I mean, with this much, you know, I mean, it's trying to find patterns, and then we don't have a lot of data to make these patterns on. You know, it's tough to wrap your head around, I think, but Julie feels pretty good about it. Let's see what else we got.
Throw big data at the problem in that case because you don't have it. It can cost tens of thousands of dollars to run a new experiment, so you're not getting it for free.
Not getting it for free.
The third
I like that.
challenge and opportunity is that you have established domain knowledge. We know physics, and we can use that to our advantage. And then in terms of interpretability, the flip side of that is that we want to actually get some information back out of these machine learning models. We're scientists. We care about why they're making given predictions.
Okay. Interpretability is a big concept here. So I think established domain knowledge, that makes sense. Like if we're doing our machine learning and material science, it helps to know some physics, or it helps to know some material science, right? Like that part makes sense.
Yes, no, I agree.
Okay, cool. Just making sure I'm checking it.
I'll nod more enthusiastically so you could see that next time.
And then interpretability means that we can interpret what's going on. So when the machine learning model is making a prediction, not only do we know what the prediction is, but we know why it's making that prediction. That's what interpretability means. And interpretability in traditional machine learning applications, normally we don't really care. It's not really that important because I don't know, does it work or does it not work? I don't really care how you're giving me the information. Yeah. But pretty important if we're doing science and stuff on materials science, and we want to know why we're making this prediction. Like, yeah, take salt, right, and then put it together with some fluoride, and then immerse it in copper, and then you're going to have a spaceship material. We want to know why. Like, that doesn't make any sense in our physics models. You know, are you sure? And then we find out it's wrong, or maybe we're wrong, and you know, but we have to understand why, as we don't really with big data. Yeah, like traditional machine learning, big data stuff.
Yeah, no, and interpretability is super important because it's just like she said, like, we're data scientists. We're not just coders when we're looking at this. We're trying to solve this from a scientific standpoint. And if you're not able to replicate or understand something in your scientific method, then it was a fluke. So being able to get that data back and being able to do it consistently and understand it thoroughly is really important. So that way we can find different ways to do it. So instead of salt, we can mix MSG or something else in there to see what other materials we can get to see what plays the biggest factor in something. So being able to replicate it and understand it is very important.
Yeah. I think that makes sense. If we were doing machine learning on like basketball games, and then the machine learning people were like, yeah, your best plays is just have everyone stand under the basket and throw it from full court. Like, if we have basketball knowledge, we're like, okay, this model is wrong because it doesn't make any sense. And it's easy to see in basketball, but if it's like super complex chemistry of materials, like, unless you have that domain knowledge, you don't know what's going on. Like, you wouldn't be able to tell fact from fiction in that instance. So you need domain knowledge, which also is interesting to me because normally, like, I don't need any domain knowledge at all in advertising to figure out what ad is working well on a website. You know, it's just A/B testing sort of thing. So I think that that's a nice, interesting paradigm shift as well. I think we're at number 4 times I've said paradigm shift. 3 or 4. If it wasn't 4, now it is. Okay, here we go.
We also really care about uncertainty quantification. If Netflix gives you a recommendation for a movie you don't like, it's not the end of the world. You can just pause it. But if you've already invested $10,000 in an experiment because you thought it was going to be great, but the model just really didn't know, then you've just lost that money. And then the last is the
point.
prediction task.
Do we need to stop there? Uncertainty quantification? We want to know how sure we are about something, pretty much.
I mean, it kind of leads back into what we were talking about with interpretability and domain knowledge. It's just like, do we understand it?
Yeah.
And
how sure are we about this?
yeah, exactly. Like,
yeah.
Do you think chocolate's going to be good on this sandwich right now? Like it's got a lot of salami on here. Is this the right move? That's the way I'm looking at that.
You're saying it's good to go, but I really need to know. This is you don't understand.
We're
not just trying to do.
Producer Wolf, hello, you guys seem big brain. Can we combine machine learning with cybersecurity? Was making a model, was looking for advice. Well, stick around, Producer Wolf. Maybe someone in the chat will be able to help you. If there's anyone I know who knows about machine learning and cybersecurity and all those sorts of things, yeah, actually jump into the Discord. I'm going to throw you a link to the Discord, and then we can chat about that afterwards, and we'll get you set up. We'll help you make the world a safer place. Let's keep going.
Simple pattern matching in many cases. So if you've trained a neural network to distinguish between photos of cats and dogs, then you've trained it on a lot of photos of cats and dogs, and then you just give it another photo of a cat or a dog. That's not what we're trying to do. We're typically trying to find materials that are better than anything in the training set, right? We're trying to extrapolate, and that's fundamentally a different goal. Okay.
Yeah, that makes sense. We're looking for.
Pause that. I like that a lot. I like what you just said. That's pretty dope.
That is really. Hit me with it, Jordan. Hit me with your.
First, Producer Wolf, we have it at 1.25 speed. We swear she's not just trying to like throw up the information at us. We just wanted to make it so when we press play, it's exactly. So it's coming a little quicker. I think it's really cool what you said, because most machine learning models are just trying to predict whatever we're asking for it. So I worked again with this team of amazing people on a housing prediction model, and it just guesses what houses are going to be worth due to square footage and stuff. So being able to make a model that's not just predicting the same, but trying to predict something better, trying to think beyond what it's trained for, is really interesting, because it's going a step further than what traditional machine learning has done. It's guessing, but it's also following all these rules. So it's educated guessing for us, which I think is amazing.
Yeah. Machine learning model. Here's a bunch of data. I want you to come up with something that doesn't look like any of this. Mm-hmm. And from a machine, that's kind of like, I don't know if I can do that. I don't know. I've never done that before. I know cat and dog. I can pick cat or dog. I can't pick a horse. I don't know what a horse is. But here we're telling it, no, we want you to get us to horse. Here's cats and dogs. Get us to a horse. And apparently we're able to do that. Kind of crazy.
Now I'm going to dive into each of these different rows in a little bit more detail.
Yay, let's dive in.
You know I'm a data scientist because I organize everything into a table to begin with.
Did you get... I want to lock in on that joke real quick. You know I'm a data scientist because I organize everything in a table to begin with. To the tepid reaction of the crowd, I feel like the crowd could have helped her out a little bit more there. I thought it was a good joke. I'm gonna be straight up. If I went to this thing, I'm not there to laugh. I'm there to learn. That's true. They might be like in a bunker, like just like in shelled with this information, like just trying to keep it all together. And then the person who laughed,
like gamma rays to the Hulk. I just want to get bombarded with it, and let me just soak up as much as this as I can, and see if I understand it, so I can go tell people in the streets about it. Like I just
on the streets, no, exactly.
Like, do you understand how we're using machine learning for materials? And they're gonna be like, bro, this is Whole Foods. Like, please, like, can you hurry up and leave?
Sir, there's a line behind you. Sir, please put back on your mask. All right, let's look at this data type thing going on.
So in terms of data type, as I said, this is highly heterogeneous. We've got all these different data sources, and not all of them, it's not always clear what to do with them. For example, I'm sure that many of you are being powered by caffeine right now. That's how you're making it through a PowerPoint.
Always.
And but what do you do if this is the input to your machine learning model? How do you use that as an input? It's not a fixed length vector.
No, that's a funny thing. If someone gave me this thing on the right, this chemical compound, like, what do I do with that in code? Like, what am I supposed to do with that? That's really, when she said that, I was like, yeah, I have no idea what I would do. I don't even know what I'm looking at, but it's a fixed length vector.
Come on, you don't see what to do right there? No.
That's you just got to go. and then you're done.
Just make the thing, and then it'll learn it, and then you have new elements.
It's just code. I think here, fixed length vector, tell me if I'm wrong, people in the chat who know more math than I do. I only know a little bit of linear algebra, but it's like a set of points with a fixed space. It's not like infinite space and infinite points. It's just like a fixed length. It looks like that, where we definite endpoints and a discrete number of points. Like it's a limited amount. Does that make sense, Jordan?
A fixed length array. Thanks, Thoughts Underground.
Fixed length array. Who said that? Yeah, Thoughts Underground, of course. Just freaking slamming it. I ooped it, and they alley slammed it. That's what they say, right?
Let's keep going.
But luckily there's
Cruel Crusader. Yes, it is chemistry.
It looks a lot like chemistry. Yeah,
we're materials, science, like physics, like that. That's what this is right now. It's all the things, and then we have to.
It is. It's all coming together. That's crazy. I didn't think about that. It's chemistry, physics, code, all together in this one talk here.
At the same time. And we're only 8 minutes in. It's great.
Yeah, only 8 minutes. I hope you're ready for a long one. No, I mean, we'll keep going. Computational data, synthesis data, processing data, composition information, microstructural information, all of these different types of data points, we want to be able to do something with all of them in the same model. So not just click data, but we need this computational data. And then we have this processing data over here. And then we have the synthesis data over here. It's all kind of crazy. And we want to put it all together. So let's keep learning about this.
A lot of readily available libraries for things like molecular structure to transform this into fixed length vectors based off of number of aromatic bonds, things like that. So people have already
which is great. There's a library to do something with that molecule with code. There's a library for that. Makes sense. Nice.
In their domain knowledge.
Of course there is.
And started to bake it into open source libraries for how you can translate chemical formulas, organic molecular structures, etc., into features that are useful for machine learning. And that process is ongoing throughout the field. So there's a lot of active work on how to transform synthesis data into also fixed length vectors or something usable by machine learning. One of the ones I'm going to talk about a little bit more now is microstructural information.
Microstructural information. Cool.
So for those of you who don't have a background in material science, material microstructure is looking at things like grain boundaries and defects, and those have a huge impact on the ultimate material performance. So if I just give you the composition of an aluminum alloy, that actually won't let you know what the strength of that aluminum alloy is. You have to also know the microstructure. And the microstructure is typically determined by the processing steps. So what heat treatments, et cetera, the alloy goes through. So if you talk about a specific aluminum alloy, you also typically give the temper, which was the heat treatments it went through.
Okay. I'm cool. Are you cool?
I'm pretty hot right now. Yeah, no, I'm cool. I kind of like where this is going. If I'm thinking that I'm thinking right.
Yeah. Let's get a little bit farther into this.
Yeah, that's
and so people usually measure the microstructure using something like a scanning electron microscope and SEM. And so they get out an SEM image, and then they want to say,
okay, SEM image is an image we get from our scanning electron microscope.
See, I was gonna say super electron microscope, so we're there.
Okay, yeah, I was gonna say
learn how to ride the bikes differently, but we're still riding the same. We're going down the same path. We're there.
Yeah, super evil monkey is okay. Let's keep going.
Super electron magnetism.
And this would be something where it'd be really useful if you could use machine learning to just automatically classify what microstructure you have, or if you could use these SEMs as an input to a machine learning model to help you predict an ultimate mechanical property. So it could say,
whoa, okay, let's keep going. She's about to do it.
You could say, here's the composition, here's the microstructural image. Now help me predict what the tensile strength is going to be.
Word. Okay, that's crazy. That is crazy, though. All right, so can you see this? I hope so. If we look on the right here, these images are the microstructure of, I guess in this case, aluminum. Yeah, aluminum.
Aluminium, if any of you are from the UK or Great Britain.
Right,
Wales.
Aluminium, of course. And these are all the same image, by the way. They're just different zoom lengths. So the one top left is like super zoomed out. And then, super zoomed out, it's still like, we're looking at like electron microstructure stuff. So still pretty close. But anyway, it's kind of like wavy. It's a little bit wavy. And then we go next to the next one over, and we've zoomed in on another spot, and we can see the microstructure. And this microstructure gives us a lot of information about how the macro, or like the bigger, when we look at the really small things, they tell us how the really big thing is going to be reacting to something. And that's kind of, I think, what we're looking at here. Instead of us with our untrained human eyes looking at this, just trying to like, yeah, it looks like this, we can have a machine learning model go through and classify and really categorize and understand in depth every single pixel of that image taken by the scanning electron microscope. And then if we take that and we match that with things that we know about physics and things that we know about the macro level, we can put that together and start making predictions that are new predictions because we understand about the core microstructure. Is that, we're on the same page, right, Jordan? Does that make sense?
Yeah, no, I'm completely with you. I'm just trying to read what Crusader said in the chat. Isn't this basically how atoms hold on to each other and machine learning studies of how it functions?
Hold on to each other. Yeah. No, exactly. Yeah, that's kind of exactly what we're looking at. Are we going to be able to understand and then make predictions based off of our knowledge of things at the atomic and like electron level? I think that's a good way to put it. Cruel Crusader. He's an elite guy. And just need people that can help me. My idea is super big brain. Good luck on your idea, Producer Wolf. We can talk about it in the Discord. All right, let's keep going.
Good luck
to
with
do that, you have to be able to use images as an input to your machine learning model. Luckily, there's been a huge amount of work in using images as inputs to machine learning models, specifically for
we got lucky, Jordan.
I know.
Convolutional neural networks. So convolutional neural networks are a type of neural network that were specialized to use images as inputs. And so what we did in this case is we started with a database of SEM images for which we had labels. In this case, the label was the specific microstructure that was present in that image. And we passed it through a convolutional neural network just to create features. And in this case, what's different about microstructure from images of cats and dogs is that in microstructure, what we care about is the textures, right? We're not looking for a specific object, we're looking for the textures. And so there's this idea of translation invariance in that. And so we looked at different texture featurizations, which were basically just translation invariant features of what was present in that image. So convolutional neural networks, they have different...
Kind of lost me with those few lines, but I'm still with her. Yeah. It's just these people, these PhDs, they throw around a word like featurization, and that's not a word I've ever heard before, but I guess, you can just, you can do things. That is a word. It is now. I mean, I believe her. I believe it's a word, but I've just never heard it. She has a
PhD. She could make up any word she wants, and I'd be like, of course,
Oh, featurization, of course. Yes. No, I mean, it makes sense. It's the... Let's keep going here. The texture featurization, meaning all the different, what do we have?
That's how schools make
the max,
exactly.
Grams, the Vlad, which I think is a type of light type of thing. Let's keep going. Let's see where we're going.
Filters, and they're looking throughout the image to see if that filter is activated. And so they might have a filter that's looking for a circle, for example, and it's looking everywhere in the image to see where that circle is.
Oh,
and then one of the features we looked at was taking the mean of that filter activation across the image. And the idea behind that is we don't care where in the image a circle is. We just want to know if there's circles in the image.
Oh, okay.
And then the output of this feature.
Okay. We have, because the CNN has all these different layers in the model, and the different layers are going to be looking for different things in our microstructure. So just one layer is looking for circles, and then did you find any circles? And all these different layers are looking for different things. Okay, that's what she's getting at there. Yeah, that makes sense. That thing on the left, that's what the thing on the left with the bars, those are the different layers of the machine learning model that's getting passed through. The thing on the very left is like the images, and then they go through, this is what's going on. They go through all those different layers, and as it goes through those layers, we're building on more knowledge or more understanding about what's going on in that image with the texture featurization. That's what's going on, because we're now we're looking at the textures, and we're saying, all right, these are the different features of this texture. This texture over here, it's got a circle. And then you go to the next layer, and this is the square layer. It's looking for squares. It's like, word, we got some squares in this arrangement, in this pattern. And then you put all that together, and then you get magic. I think that's what's going on here. Does that make sense to you?
Yeah, machine learning is a lot of magic, but I think understanding the diagram on the left's a little bit more good explanation. It really did help me hone in on what was going on over there because I was like, oh yeah, I like colors. And then I just kept looking at the things on the right and like, oh yeah, those are kind of wavy. So understanding that each one of those images is going through those layers and getting more information so it can categorize it, right?
Thoughts Underground says featurization is features are the things the model makes predictions off of, evaluating what things we should predict on. Right, right. Yeah. So that's, I think we're all kind of getting to the same thing here, which is it's just now we have to give it some things to make our predictions off of. We have to give it some features. We have to give it some sort of we have to give the computer, we have to tell it what to think about. We're telling the computer what to think about. Think about circles. Tell me about circles and factor that into your predictions. Circle being a feature. That makes sense to me. Wouldn't the machine learning model need to see it under different environments to understand its properties? Yeah, I mean, ideally, I think in traditional machine learning, that's exactly what happens is we can just test this thing under a whole bunch of different environments, a bunch of different conditions. However, when we're talking about material science, to run those experiments to see how the material reacts in different environments is just, it's going to be hard. It's going to cost a lot of money. And, these science people, they're not exactly cozying up with Mr. Monopoly Man and they're just doing whatever experiments they want. They have some restrictions on what it is that they're able to do. So, and that's what this is all about, really, is machine learning. When you have no unlimited data and no unlimited money, what do you do with limited information? And that's what I think is so interesting about this, because we have to use our domain knowledge, and then we have to use a little bit of machine learning, and we have to use a little bit of caffeine, a little bit of luck, and we put them together, and then we're able to get something that's useful. I think that's kind of what's going on here.
A little caffeine.
The poll is going on today. Yeah, answer the poll. Today is goated. At least I think so. But yeah, answer the poll. Yay.
Is then a vector of textures, where it's saying, here's the textures that are present in this image. And we can use that as an input, in this case, to a random forest model, to train this model on classification for which microstructure is present in a given image. Now, one of the key questions here is, what layer of the neural network should we take our features from?
Yes.
Because there's a lot of convolutional neural layers in these networks. There's a lot of filter layers. And so it happens that the deeper you go into the network, the more complex the textures are that you're starting to look for. So I've given here a sample of what some of these textures look like for different depths of the network. So this is a very early layer, and then a much later layer. And you can see that it starts out looking for very simple textures, wavy lines, and then it starts to get to very complex patterns by the time you get deep into the network.
She says pattern. Excuse me. She says patterns. Do you recognize that thing on the bottom right as a pattern, Jordan?
Maybe not to me and you, but compared to other different images, I mean, because we have to remember the machine learning is taking a bunch of something and then comparing it to something else. So maybe it's just trying to use these layers to understand what that even is. I mean, it looks kind of like when you close your eyes and you push against them really hard, you start seeing weird shapes and stuff. It looks like that to me. And,
yeah, it does.
And like peacock feather kind of things in the bottom too, but to it knows a couple hundred other images that look just like that. And we're trying to train it to understand why. And if we see anything like that, what does this mean?
Yeah. If you told me to find a pattern in that bottom right image, I would think that I'm going crazy.
Totally. That's super easy for you. Yeah. I mean, at the beginning of the lecture, you helped her with this whole thing.
Yeah, I was the one who introduced her, actually. Yeah. I couldn't make it to this talk. I called, I said, Julie, can you do this talk for me? I can't make it. And
I really need a sandwich.
And so what this is plotting here is the accuracy of a model that's trying to differentiate between these three microstructures. So this is a steel data set. So this is a network microstructure. Let me move the mouse.
Yeah,
a spheroidite microstructure and a perlite microstructure. And so we wanted to distinguish between these three microstructures. And we took features from different layers in the neural network. So this is an early layer and a later layer. Mm-hmm. And this is the model accuracy. And the different colors represent different texture featurizations. And what we can see is that across all the different featurizations we tried, it doesn't really matter what featurization we use, as long as we use the features from the correct layer. That it really wanted the features from these later layers, because these are relatively complex textures. They're not simple. Okay. And so for this particular problem, it's saying please give us access to relatively complex textures.
Yeah, I got you.
Now, one of the other things that I think is really interesting when you start...
I got you. It wants the images. It wants the bottom right image from the previous slide. It wants the really zoomed in version. That's what she's saying. That's what the model prefers. Cool.
Apply these methods, these deep learning methods, to physics problems is the question of interpretability. Now we have a model that's able to distinguish with very high accuracy between these three microstructures. How is it able to do that? And so at the bottom, what I'm plotting here is the characteristic texture. So this is now from the neural network. And this is what the neural network is saying is the texture it's using most to distinguish between the network microstructure and the other two microstructures. And
those
similarly
like
for
cells.
spheroidite and perlite. And this is both informative and reassuring. It's informative because it's saying, okay, in the network case, it's mostly looking for cell-like structures versus white dots versus interlocking wavy lines. And it's also reassuring because that makes sense. You look at the top image and you look at the bottom image and you say to yourself, okay, I can see how it's doing that.
Yeah.
And so if you're trying to look at a model and you want to make sure that you're not just suffering from sample bias or from some kind of false signal, this is a really good way to do that. For example...
Okay, cool. This slide, and I think the next slide, and then we'll be out of here. I don't want to take everyone's time. I could be here all day talking about this. But yeah, no, that's... See, I think this slide is really cool, though, because it shows us exactly what it is the machine learning model is looking at. We're looking at that top image, and it's like, you know what you got going on here? It's kind of like cells. So it kind of looks like this. And then it's like, oh, yeah, no, that makes sense. I can see how you got that. And then spheroidite.
I'm going to let you butcher that. I'm not even going to jump in. Let's just...
Spheroidite. Spheroidite. And the spheroidite image.
I've heard of this one. It makes really good pasta sauce.
It makes it a pizza. So in the spheroidite image, we have what structure you got going on here. You got a lot of dots. Like word. Yeah, that makes sense because when I look at it, I see a lot of dots. It kind of looks like an asteroid. And then perlite's really interesting because I wouldn't have seen that interlocking thing. I would have seen maybe some line, but interlocking is crazy. And I would assume that that's pretty strong too. Cells are pretty crazy too. Have you ever looked in a microscope, Jordan?
I have.
That's exactly what it looks like, right? Those cells.
Our eyes can't see it, but when you start zooming in on stuff, it's ridiculous. Like,
I'll tell you, brother. Let's see. Anything in the chat? Let's see. Interpretability, why the model behaves the way it does. Understanding the model's output. Yep. I would say so. It could even be rotated. Look at the top left and two on the right. They don't look like they are oriented the same. Was that the last one? Last image? I might have missed that. I feel like interlocking would be brittle. Yeah, maybe it's brittle. I guess I could see that because it's interlocking and then it's like extra pressure on every individual thing. Yeah, maybe that is brittle. Maybe you're right. Unless it's flexible. But that's what material science is all about. All right, let's keep going. Am I missing anything else? But go. Yeah, it is goated. I feel like interlocking. All right, let's keep going.
If in this image I had just seen scale bars, I would have known that, oh, I didn't process my data correctly. All of the network data still had scale bars on the SEM image.
Yeah, I think this has to be more flexible too.
So this is a really useful way to check for errors in how you process your data as well as to gain scientific insight.
Cool.
So this is just to say that for each of those different data sources I mentioned, it's not always straightforward to use these as part of a machine learning model. You have to use some creativity and some domain knowledge to think about what does it take to take your chemical formula or your organic molecular structure or your SEM image and use them together for a machine learning model. Each of them requires some custom feature engineering.
Yes.
So the next step is data volume. So now that you have your features, you want to start to use them for a machine learning model. So ImageNet,
I'm going to speed run this part. Data volume. We don't have a lot of data. That's kind of what we're going to be talking about.
Okay, great.
Yeah. Because I want to get to this one story that she talks about that I think is really, it's a funny story. It'll be something nice to go out on. And then I'll put the link in the chat for this for everyone to enjoy. And then we talk about machine learning models, DFT band gaps, and this is like.
There you go. Come on, you can tell me. I believe in you.
Yeah, I'm not gonna lie. This part got a little bit sketch for me, but I think it's just the difference between our direct observations and what our machine learning model is giving us. So the farther we go to the right, the more data we have on our experimental data set size, the better, the less distance we have between our observations and our machine learning predictions. I think that's what's going on. But I want to get to the story about the doggies. Where are we?
I love
Where
dogs.
are we? Did you get to that part? And this is just going to be a nice outro story about anything to do with machine learning and data science. So if you haven't seen this, if you haven't heard this story, you're going to like it. I liked it a lot. Dude, imagine if I sat here and tried to explain all the dude. It's a good thing.
Oh yeah, no, this is from Dungeons and Dragons. That's the deep right there. And that formula is what you use in order to cast your spells. It's really simple. I can go over this in the Discord if anyone's interested.
All right. Since Thoughts on the Ground was talking about interpretability, here's why interpretability is important. All right, here we go.
In order to have a well-fitting model. And so then the last part here is, okay, we now have a model that's performing well, it's obeying our known physics. How can we interpret its predictions? What can we get out of this model? And so why is interpretability even important? Well, as I mentioned earlier, it can be useful for debugging a model. It also is really useful for building confidence for the model in regions of interest. So before you go out and perform that $10,000 experiment, you might want to have some understanding of why that prediction was made so that you can build confidence that it was made for the right reasons. Furthermore, and this is the most compelling one for me, is it can help you build scientific understanding. When I was working in turbulence modeling, we started to come up with models that were more accurate than the theoretical analytical models that people had been using for decades. And the question is then, okay, if we're starting to come up with models that are better than what the best experts had been thinking about for years, what did the models know that we didn't know? What can we learn from these models? And so I think it's really important that we approach these with a little bit of humility and admit that we're able to learn something from the data that we didn't just think of ourselves, that maybe the machine learning models were able to come up with.
Makes sense to me.
And then the last is understanding model sensitivity. If you make a prediction, you might want to know if it's robustly optimized or if you're right near a performance cliff.
Yes.
And so the pictures here on the bottom, these are talking about, these are from a paper by Ribeiro's group et al. At University of Washington. This is an example of why it's important to use interpretability for debugging a model. They were training a
I like this story.
classifier for huskies versus wolves. And so here's a husky on the left that it correctly classified. Here's a wolf in the middle that it correctly classified. And then on the right is a husky that it got wrong. And so they used some interpretability analysis to say, okay, was it the muzzle shape? What is it that we got wrong? Because our classifier is pretty accurate on our training data set. And they found out that the model was only looking here. It was looking at the snow. They developed a very good classifier for snow because it turns out most of their training data set had wolves on snow and huskies on dirt or grass. And so it's just, and that's a funny example.
Isn't that a cute, funny story, Jordan?
So I got a couple stories now that I'm just gonna bombard you with, but it's
Hit me.
Awesome. I was on everyone's favorite app, TikTok, and I saw this video of this person acting out an article that she read. Basically, they were like, "Hello, you're my new machine learning algorithm for donuts." And then she's like, "Is this a donut?" And the AI's there, it's like, "Yes." And then it's also like, "That man has cancer." And then they're like, "Wait, what?" And then they're like, "Is this a donut?" And they're like, "I have no time for donuts. That man's hemoglobin levels are through the roof." And then it plugged an article saying that they made a machine learning algorithm for donuts, but it like accurately predicts cancer in people. Like it's some crazy thing like that. And I think that that's awesome because it's like we have all these intentions and we think we're doing everything right, but in reality, we're just guessing. And that's the best thing about it. And that leads into my second story where it's talking about how we fundamentally don't fully know any one thing, and that's okay. Because if we think of everything as a big circle, and that's if we knew the whole pie of everything, the way that we know things is more kind of like a pentagon. Like it's close enough in shape.
I love that.
But there's some rough edges so that we still don't understand. And so getting these machine learning models to teach us what we don't know can just help us further make these models better to keep teaching us, or they can teach us things that we didn't even think about. I mean, literally this whole dog thing is freaking hilarious to me because it predicted snow so well. And I was like, that's cute. It's funny. And like you said, it's a bit of humility when like you look at this, because we have to understand like we aren't these programs, we are still people. And so they probably didn't understand the entire time how this thing was working. They're like, it just works. And then when they look into it, it's like, oh, it's looking at snow. which is it's cute, it's adorable, it's
Yeah.
something to like let everyone laugh about. Like it's a good moving on point, but it also shows us that we still don't have the full circle. We just keep adding edges to our shape until it gets formed into a circle.
It's like a yeah, and in some aspect, it kind of means that the data, wasn't cleaned enough, or they didn't consider, their data inputs. But to me, it's hilarious. It's just like a kid who somehow gets all the right answers, but you're like, hey, how'd you get that answer? And they're like, oh, dude, every single test this semester has been BACD. It's just been
Yeah.
BACD the entire time. So I'm really good at answering BACD.
In high school, we had to take a big test, and one of my best friends came up to me and he goes, "Whenever you're stuck, never forget abacadabra." I was like, abacadabra, and it's like ABACBDAB, and I was like, "You're kidding?" He goes, "I've gotten this far off of abacadabra. It has not failed me since. I will not give up abacadabra." So, I mean,
yeah, here's Jordan, our resident 20th century American literature expert, who's done so well on every test. Well, it all starts with abacadabra, really, and
that's my novel series. You can get it, and it talks about advanced machine learning with material discovery, and it's just abacadabra, a way of life.
Computers are they're so smart, and then you give them all these pictures of wolves and huskies, and you're like, can you tell the difference? And it doesn't even consider the wolves. It can't even get there. It doesn't even know what you're just like. I can.
Snow.
Bottom left is what you're looking for, right?
No, snow. That's it. Thousands of dollars, right?
Is this the husky in the bottom left where the green is?
Bottom left equal husky. 0-1. But I think
I know of a husky. It's green. It's very thin. It grows up from the ground. I know what a husky is.
When no green, no husky, and when wolf. The way I'm looking at it now is, if we did have to clean this up, how would we do it? So I would like try and isolate just the image of the dog, maybe, or the wolf, and then train it off of that. So that way it's not looking at the bottom left corner. It'd have to like take some recognition into maybe like fur pattern, kind of like we were looking at with the material discovery.
Crop the image. Yeah.
Or something like that. Or maybe like tail floofiness, like there'd have to be like some parameter in there that it would learn better off of than the other. So that's what I would do if I were looking at this. I would try and go for maybe more of a cleaner image, like we said earlier. Yes, floofiness. Yes, the floofiness of the tail. It would be very important because you can see the floofiness of the first dog. This is my lecture now. The floofiness of the first husky. You can clearly see that that's a good floof. Whereas on the wolf, it's more of a streamlined floof, kind of like one of those dusters from the 70s. And the prior one's more kind of like those peacock dusters that my grandmother has. And that's how we would distinguish between wolves and huskies. That
would work. I feel like that would work. And with that, we are at 8 o'clock. So unfortunately, we're out of time today. Oh, but that's okay because we will be back again. And I'll put a link to the talk is called this. It's called, if you type in IACS seminar, Machine Learning for Materials Discovery on 11-30, you will find this talk. Today's show is GOAT. It was the GOAT episode, greatest of all time. Yay, us. So you can go ahead and look this up. I'll put a link to this in the Discord. If we can throw a Discord link in the chat again, then you can go hang out over there with me and everyone else, and Thoughts Underground will be there too. And then Thoughts Underground's about to have a show, so that'll be really cool. And Cruel Crusader says, apparently B is the right answer in multiple choice questions. Yes, I agree. I always put B if I didn't know, because my name starts with B, and I thought that would be nice. B for Brian. If I don't know, it's B for Brian. And John X. Brand throwing a raccoon in the chat. Kind of looks like a husky if you look at it a certain type of way. The machine doesn't know the difference. And Brian Jordan, are the GOAT? No, that's you, Thoughts Underground. And also us, and also everyone here. Also Cruel Crusader 1337. John X. Brand is goated.
Before we head out, do you see the poem?
The poll?
Roses are red, huskies are green, wolves are white because snow. Thank you all for coming. That was so awesome. I love it so much. It's so accurate.
Yes. All right. Well, thank you all for coming. That was today's Tech Topical Tech's Best Talking Show. A special thank you to our esteemed guest, Jordan Torres, JT, as they call him in the biz. And I'll see you all. You know what we got coming up? I just confirmed it. It's going to be happening. We are having our talk with government and computer science and these technology and government. How do these two things mesh and mold? And we're going to be talking to a real life politician. Can you believe it? It's going to be so cool. It'll be happening next week right here on Tech Topical, 4 o'clock Pacific, 7 o'clock Eastern Standard Time. And I will see you all next time. All right. Bye-bye. Thanks, Jordan.
Bye, everyone.
Talk.